No, I was seeing that. So now in very bad shape.
Ready?
I think so.
Hey. Morning.
Very bad shape.
Wow, Bob, you're power. What did this change? And anyone understand? Wow, Bob, you're power. Maine, we get a, we're taking a blue moon. Blue moon, it's gonna be on May 31st. It's the first time we've had two full moons in the sky since 2023. It's a very rare occurrence. Hence the name blue moon, right? Our 2026 blue moon is also gonna be a micro moon, which is the most distant full moon of the year. It's about 7% smaller than the average moon. June, two of the brightest objects in the sky, Venus and Jupiter, will be in conjunction. They become visible at around on June 9th. That'll be the closest approach. It'll be about 22 degrees above the horizon, starting around 8:45 on that day. On June 13th, we're gonna have our annual pizza party at the museum. Bubble supply pizza and beverages. Attendees are encouraged to bring a dish of their own. August picnic tentatively Saturday, August 22nd, with a rain date the following day, and it's the Boonton RBA fields.
Town, the RBA fields at Boonton Town.
What does RBA mean?
Radio.
Okay, sorry.
It's an old airfield over there where they actually did a lot of science and technology with radios and radar and stuff. And it's actually, it's a beautiful site. It's actually it's very well known as the athletic fields at Boonton Township. I mean, the space is absolutely enormous. I have reached out to the recreation director, Boonton Township, haven't heard anything back yet from them. So this is all tentative, right?
Right, August 22nd, Saturday.
We're hoping for the date. Those are the dates we pegged. That hopefully they give us the good sign on that.
Okay, we have the month of June, July, and August. We have 5 outreach observing programs, thanks to Jeff. He's running that program very well. It'll be June 2nd, in Parsippany Troy Hills Library, June 23rd, Harding Township Environmental Commission, July 10th, Pequannock Township Library, July 31st, Roxbury Township Library, and August 18th, Somerset County Library. The ones on July 10th and July 31 are sold. You get more information on our website. Our website or the Facebook page.
All the way above.
The treasurer position is still open. We really need a treasurer, and be grateful if anyone would step up and take that position. Okay, over to Nina.
Right, so thank you all for coming. It's our last speaker series for the spring, and then I think most folks know that we will take a little bit of a hiatus, although we have a lot of outreach and other activities until the fall for our speakers. So just to give you a little bit of a heads up, get it on your calendars. September 12th, Saturday, here at the library, we will have Professor Don Lin speak about a sky map app and the northern sky of Egyptian pyramids in 2500 BC. And then on October 10th, here at the Morris County Library, Dr. Emily Rice will be presenting. She is an astronomer, professor, and creative science communicator in New York City. She is an associate professor at the Macaulay Honors College of City University of New York, and also an associate researcher at the Department of Astrophysics at the American Museum of Natural History. She studies low mass stars, brown dwarfs, sometimes called fail stars, and directly imaged exoplanets by analyzing their spectra and modeling their atmospheres. So fall will be interesting, and then we'll have a November speaker as well, so get that on your calendars. Today, we really welcome Charlie Bracken, who's doing somewhat of a tour, it seems like, a lot of speaking engagements recently. He is author of the Deep Sky Imaging Primer, the Astrophotography Planner, the Astrophotography Sky Atlas, and most recently, the Astrophotographer's Universe, which we're lucky to also have available here today. Today, he's going to talk to us about imaging every deep sky object, so you don't have to, and lessons from his journey. So we have a lot to learn, and I'm really looking forward to it, and we welcome Charlie Bracken.
All right, so first quick poll of the audience here. How many of you do imaging? Got a few. And I assume some of you also just look through the eyepiece on a telescope? Yeah. Okay, so I haven't looked at the eyepiece on a telescope in like 4 years, I think, at this point. I am primarily an astrophotographer. And I'm going to talk to you about this journey today. So I'm about an hour and a half away. I'm down in Bucks County, Pennsylvania. There we go. Okay, so I'm down in Bucks County, Pennsylvania. I image mostly though remotely. The light pollution has gotten pretty out of control where I am. It used to be pretty good. Now it's not great. I do narrowband imaging. That's my backyard. But I have telescopes set up in Chile and Utah, and that's actually most of the pictures you're going to see today come from those telescopes. These are some of the books that I've written. I've taught a lot of people, I think, how to do astrophotography. I started doing this over a decade ago. So today, we're gonna remind ourselves how great the technology we have is, with a little affirmation that I like to do at the beginning. And I'm gonna talk about the situation I got myself into. And then I'm gonna structure the rest of the talk to go through the deep sky catalogs. I'm gonna do a little less in this talk in the interest of time about the people behind them. But I'm going to use that structure because that's what I had to do when I was writing the most recent book. And we're going to structure the rest of the talk around that, but show a lot of pretty pictures. If I've learned one thing about delivering public talks, it's you got to cram as many pretty pictures of deep sky objects into it as possible. And I will try to meet that goal today. So this is the affirmation I was talking about. We had it really easy, and I'm guessing there are some people in the room, maybe you did film astrophotography. I thankfully never had to do that, but just to show you, right, so E. Bernard in 1895, this is one of the first images of the California nebula. You can only imagine what he had to go through to take that on wet plates. And then, it took 6 hours. He actually, from his location on Mount Wilson, had to ride a mule up to the top, drag the water with him in barrels so that he could drink and also develop the plates on Mount Wilson. I set my computer up in the backyard to run, went to bed, and woke up the next morning to process some data. So things have gotten substantially easier. When I was a child, this is what got me into astrophotography. So when I was a child, I remember seeing this particular cover of National Geographic. This is an image by David Malin, a pioneer in color astrophotography. Wow, like what do I have to do that? I wasn't able to execute on that because I couldn't buy a telescope and have all the equipment that I have now for decades. But that was my early inspiration. And again, like David Malin, like this is pioneering work with unsharp mask and all the different color work that he had to do. Again, I could, from my backyard, can what I would say is arguably at least as good of an image in a few hours. So we are in a golden age of astrophotography. When you used film, maybe 1 to 3% of the photons that struck the colloidal silver would actually register. Today, about 90% of the photons in most, at some frequencies at least, some wavelengths will be captured by a CMOS sensor. optics and cameras are getting cheaper every year. A lot of this is getting automated now. Filters that used to be a really super expensive. Those have gotten a lot better. You can program your system to run while you sleep. We have amazing processing now that you can make stars disappear to process the stars and the objects separately. And like I said, it's not cheap, but you can have a telescope under dark skies in the desert somewhere and access that, control it, and bring the data onto your home computer. It's gotten to the point now where amateur astrophotographers are actually discovering new things. So if you follow AstroBin, there are constantly amateurs on there discovering new objects, in particular planetary nebulae, these really huge supernova remnants. I mean, the goals have gotten absurd. People are taking 200-hour exposure time images now. So really, we're moving things forward as amateurs. But I call it this situation. So how did I get myself into this? Where I was writing the book that we're going to talk about. A few years ago during COVID, I was working with my co-author Max Whitby, and we had a telescope set up in Chile, and we started taking a mosaic image of the Milky Way. This is really pretty. And of course, then the thought occurred to me, what if we just kept going? So we did. This is an image of the entire night sky. So this is a 153 panel mosaic. It's 1 gigapixel in size, and that's actually scaled down 4-fold from the original resolution. It is, the northern hemisphere was taken from Spain. The southern hemisphere was taken from Chile. It took me about 4 months to actually do the work, processing it to get it all together, remove the gradients and everything. And you can see I've enhanced the H-alpha signal. So this is regular RGB color with H-alpha overlay. So you can see a lot of things you might not normally notice as much. So if you get you're orienting yourself, you probably notice Orion over here. So there's Barnard's Loop. There's the California Nebula. That little spot right there, that's the Pleiades. And 31 over here. But it reveals some stuff you might not normally think about. So this is this giant thing down here, the Gum Nebula in the southern hemisphere, Magellanic Clouds. This is the Zeta Ophiuchi Nebula. So some stuff shows out with that's just so big. These are, you need like almost wide angle lenses to capture a lot of these objects. And it just kind of reveals the scale of our night sky and what it would look like if we could see a hydrogen alpha better.
Why isn't it flat?
Why isn't it flat? Because this is similar to, because it's projection is the short answer. So the same way, this is similar to like a map of the world, like a Mercator projection. Because the Milky Way would be at an angle, like this is sort of mapping. If you were to plot RA and DEC on this, it would look like a grid. And so that's just the distortion inherent in any projector. So Max and I used that as a foundation for a book, and our idea was we'll sort of do a modern Messier catalog, but for astrophotography objects. So we had 110 of the best objects. We published that book in 2022. And then, because I can't stop, I said, I wonder if I can do all the deep sky objects. And that's the project that I just completed and published this year. It's called the Astrophotographer's Universe. It is a very large book. I have copies over here if anybody wants one afterward. 728 pages, 1,700 plus objects, over 1,000 color images in it. And the idea here was to say, if you're an astrophotographer, what is worth imaging in the night sky? We'll go through some of the stuff that I did there. So hopefully you get the benefit from my insanity in doing this. The process I had to go through was figure out, start with all the objects and distill them down. So if you go online, there's a website called Vizier, you can find there are 27,000 astronomical catalogs. So you're probably familiar with the NGC, Messier catalog, things like that. There are catalogs for everything. There are super obscure ones. I just noted on here, 115 were added in the past month. There's about 20 million objects. Of course, there's a ton of duplication. A lot of these are radio objects, things like that. But I had to start somewhere and distill it down. So we're going to go over some of the deep sky catalogs that many of you might not be aware of. So the history of deep sky catalogs starts all the way back with Ptolemy and Al-Sufi, who noticed that there were things in the night sky that were not stars. There's just a few things that they noticed. That no one was systematically trying to catalog these. That didn't strike anybody as something interesting to do. But I'm gonna set these aside because these objects have either turned out to be, a few of them are erroneous, but a lot of them just acquired the names that we use now much later on in history. So the first two, you're certainly familiar with these, the Messier 100, now modern Messier of 110 catalogs, and the NGC, which has almost 8,000 objects. These were all done with visual observation and with incredibly talented. It's amazing when you think about the size of scopes they were using, how acute their vision was, and how hard they worked and sat out in the cold to identify all these objects. Photography comes in the late 1800s. You get the index catalog, which adds 5,000 objects. Barnard's catalog, and I talked about all that he went through to take his images. That is just a catalog of dark nebulae. Then these are some of the primary catalogs we use today. These all came about in the 20th century, and this is going to kind of be the structure for what I'll go through later. So my goal in this presentation is we're going to go through some of the highlight objects from these catalogs, and then we're going to go through what I think are the overlooked ones. So in me going out and trying to image 1,700 objects and research many, many more, some of these are much more interesting and don't get enough attention, and I want to draw your attention to them. And then there are other catalogs, lesser used and often substantially overlapping with some of the objects in the catalogs we've already talked about. But this just gives you a sense of, I put, how many objects there are in each of these catalogs, and I kind of cleverly arranged them in something that looks vaguely like a periodic table so that I can call it the periodic table of object catalogs. So how many objects are we talking about? Well, if you add up all the numbers on there, and you take out the UGC, which is the Uppsala Galactic Catalog, which has 13,000 objects. The BDSL, that's a catalog of every object and star within the Magellanic Clouds. Even if you exclude those, there's still 27,000 objects. Well, that's just ridiculous. That's just way too many. So which ones are practical to image? That was the challenge that I had. So we're going to try to make some order from the chaos. I won't go into the details here, but one of the first problems to solve was deduplication. So there are a lot of overlapping objects. So, you're probably well aware, all the Messier objects except two have an NGC designation, right? So you got to go through and deduplicate. Then you got to figure out which catalog you're going to call it, which name you're going to use as the primary. Then you got weird situations where objects overlap. The Lens Dark Nebula and Lens Bright Nebula catalog, LBN and LDN, have this challenge that they're self-overlapping. So Beverly Lens, when she cataloged these objects, would catalog subparts of the objects and then a group of them as a group, as different numbers. So trying to figure out all of that, took a little while.
Used AI like that.
I used AI to create this particular chart here. So I did it all manually through the process, but then to create this chart to illustrate how the overlap was, I did use Claude for this, yes. Kind of wish when I started this, I used AI for some of the other work probably. So I had to set some criteria for what made an object something that someone might want to go take a picture of. So I won't go through all of these, but I set different criteria for each type of object. So for instance, I said, I'm gonna, five arc minutes is a good size of object to say. If you get much smaller than that for most things, you're not gonna reveal much detail, so that's probably not a super interesting object. So I said 5 arc minutes for spiral galaxies. I'm gonna include in this book every spiral galaxy larger than 5 arc minutes. And then arbitrarily I said, honestly, elliptical galaxies, they're not that interesting, they're just big fuzzy blobs. So I'm going to set a slightly higher limit for that. Say, like, most people are not going to be interested in imaging a really small elliptical galaxy. I set a higher limit there. The one place I went smaller was the planetary nebulae. So I picked every planetary nebula that's 3 arc minutes and greater, unless it was particularly interesting or was in the Able catalog. And so on. So I went through, that manually selected some of the most interesting objects from a lot of other catalogs, but fully included objects like catalogs like the Sharpless catalog, the RCW, LBN, DFW. I covered parts of those. So after distilling all of these things, like my personal answer for what is worth imaging in the night sky, including the northern and southern hemisphere, there's about 1,732 objects, I would say, that are worth at least considering your time to image. That's the number that are in the book. we've created and since launched an app that also has the 732 objects in there.
SNR,
Sorry,
what was SNR?
supernova remnant. Yes. So, yeah, supernova remnants, I mean, there are a few famous ones that are very bright, so the Cygnus Veils, one example, the Jellyfish Nebula, even in one Crab Nebula. But most of them that have expanded larger and stretched out become incredibly large and faint. So these are mostly the realm of like long exposure astrophotography. Again, this is where like, this is kind of the frontiers where you typically discovered with radio telescopes, and then amateurs have gone back, and if you do enough exposure time on that area of the sky, are finding that there's an extremely faint optical signal. So I included every supernova remnant where there is a known optical component to it. Now the fun begins. I have to go shoot all of these objects. I remeasured them, I verified coordinates, and then I did a write-up on each. Anything interesting about its history, tips for when you're going to image it. Is there a bright star just out of the field of view that's going to cause flares? Which filter should you use? What's the best palette to use when you combine those filters? Things like that. So that's the project I undertook. On the left is my backyard, so I did a lot of the northern hemisphere narrowband imaging from there. I rented that pier at Utah Desert Remote Observatories. I don't know about you, but I find it improves performance if you hug your telescope every now and then. I seem to respond well. I get better images out of that. And then I didn't get to travel to Chile, but I share a remote scope in Chile with 3 other astrophotographers. Renting a scope is fairly expensive, but actually you can split it among a few people and it becomes a much more reasonable proposition. There's also some local remote hosting options recently that have come out that have brought the costs of this down. But this project took 5 years, and the images in the book and app have exceeded 6,000 total hours of exposure time. So it's become quite a project. That exposure time varies a lot by object. So some open clusters I might have only spent an hour and a half imaging, because that's really all you needed. There are some of the objects, the supernova remnants that are super faint, 40, 50, 60 hours of exposure time. I rated each one too. Now, this is obviously going to be subjective, but I did want to provide people, if you're going to have a book and an app that have 1,700 suggestions in there, to give you some sense of what might be worth your time, given, you know, you're here in New Jersey, like me in Pennsylvania, you don't have a lot of clear skies and they're valuable. So you don't want to waste your time on something that's not going to be interesting. So I sort of took an Amazon approach and rated them 1 to 5 stars. And here's the percentages and how it breaks out. But obviously, you know, you probably know a lot of the 5-star objects, although not all of them. And these are, you know, just they're bright and they're beautiful and everything, all the way down to 1 star, where it's probably not worth your time. And the only reason I included it in the book was because I wanted to complete a catalog. So we'll talk about the classic example of that in a second. So here's that classic example. M40, right? So this is by far the least interesting Messier object. It's a double star. It is not a great target either at the eyepiece or through a camera. Everybody also knows M42, right? Like, it's hard not to take a picture of that. Like, it's just, if it's up in the sky, you probably should be imaging something else, but oh, it's right there. And every time you take a picture, even a 30-minute exposure, you know, total exposure time leads an amazing image of that object. So it's pretty clear what's really bad and what's really good. And there's some controversy in between, but at least I'm providing some guidance to people on what's worth taking a picture of. To give you a sense of how I graded them, elliptical galaxies, like I said earlier, I don't think they're particularly interesting. No matter how long you image, it just becomes a larger and slightly brighter fuzzy thing and never really looks never really looks in focus. A couple of these were 3 stars, but most of them I rated 2 stars, for instance. This is Messier 84. Open clusters. They're actually pretty nice through an eyepiece, but from a photographic perspective, don't really look that interesting in most cases, and most of them are I consider to be like a 2-star object. But a few, I'll say, like, there are some that are prettier. They're sit in the background like this M7 Ptolemy's cluster. Like I said, yeah, this is a 3-star open cluster. It's got some some other stuff going on around it that makes it really interesting, some dark nebulae, there's some ionized hydrogen around, like, yeah, that's interesting. And then occasionally you get groups like this, a really nice pair where you've got two open clusters at different distances, different densities, this M35 and NGC 2158. This is a great cluster, a great pair of clusters. I like it photographically because it gives you a sense of depth, right? And that's rare in astrophotography where it doesn't look flat. You can see like, oh, this one's closer to me, that one's further in the background. You sort of get that nice 3D sense. It doesn't come up all that often. So yeah, we'll call that a 3-star. Globular clusters. I used to play a game whenever I do a presentation. I'll show a globular cluster and say I give $20 to anybody in the room who could tell me which globular this is. Of course, no one can. My bet is always going to be safe because they kind of look the same, right? I mean, you might recognize Omega Centauri or something like that. This is M55, but they're nice, they're beautiful, but there's not a lot of differentiation between them. So yeah, mostly 3 stars, I thought for those. And then the galaxies. The galaxies are quite a problem because there's so many of them. Right, when you look at how many galaxies there are in these catalogs, and we'll go over that in a minute, there's just thousands of them, even above 5 arc minutes. You sort of set an arbitrary threshold of 5 arc minutes. I think there's over 1,000 in the book. And the small ones that are getting down to around 5 arc minutes, you know, they're beautiful. And they're especially great if you go look up a Hubble or a James Webb Space Telescope image of them. But from your backyard, they're probably going to be 100 pixels across or something like that. So that's nice, but and they're a beautiful object, but you struggle as an amateur astrophotographer without a huge telescope to get much out of them as far as resolution. So I said, okay, most of these are 3 stars, and I'm going to assume that you've got the telescope to do it. So when I gave these ratings, these are all conditional on the fact that you have the proper equipment and technique, you know what you're doing to image them. This is now your excuse if you'd like to remember this moment. I like to give all my amateur astrophotography audiences an excuse to say, but I saw this guy talk and he said I need a bigger telescope. So you can go use me as your excuse. Don't call me if it doesn't feel well. Another group of objects that I struggle with a little bit was there are a lot of nebulae. I call these the amorphous H2 regions, the red blobs. And they're older H2 regions in our galaxy where they just don't have a lot of structure, not clearly defined boundaries. They kind of look blob-like. There's a lot of them. So these are nebulae, they're interesting. You can see them with an H-alpha filter quite nicely. Usually they only have H-alpha as a signal. So they just show up as red and they're not that much to look at. So these are mostly 2 stars. There are hundreds of them. And then the last category I'll highlight here that I struggled with were really not that interesting objects, but they had really great story when I did the write-up on each one. So this is a great one. This is NGC 2419. There's a lot to its story. So it's astrophysically interesting because our galaxy stole it from another galaxy. Is a dwarf spheroidal galaxy that they believe we stole it from gravitationally, many millions of years ago. So that's interesting. I thought it was also interesting. It has a historical story because its original name, I think it was Harlow Shapley that gave it the name, the Intergalactic Tramp. And somewhere in the past couple of decades, people thought maybe tramp has changed meanings over the decades, and we should probably call it the Intergalactic Wanderer now. So not great photographically, but if you're showing someone, like you've got an interesting story to tell when you talk about that image. All right, now an onslaught of what are hopefully pretty pictures and some stories to go along with them. So I'm going to go catalog by catalog, not on all the 40 catalogs I showed you earlier, but some of the highlight catalogs. And we're going to talk about what objects you might not be aware of that are worth looking into, especially from an imaging perspective. We'll start with the Messier catalog. The Messier catalog has a well-known but very interesting story. So Messier in 1771, probably know the story, he was a comet hunter, discovered many comets over the course of his lifetime, and he wanted to catalog all the things that he might accidentally mistake for a comet while he's looking through the eyepiece. And it's pretty clear, though, that he also realized that it was worth creating a catalog of these non-stellar objects for its own sake as well. So he was the first one to sort of take that attitude. He discovered 19 of them, and he got to 40. He included some other objects from Le Caille And he had a list of 41. Lecaille had, I think, 42 objects in the catalog, and he knew he needed to beat that. So he included 4 more objects for each nice even 45. So it's kind of an even number, and he knew Lecaille had this catalog of 42, and so he put him as the best catalog, so to speak, at the time. And that is actually why M42, 43, 44, and 45 are such bright, prominent objects. He just sort of went and said, well, what do I not have? Oh, well, this everybody knows about the Pleiades and the Orion Nebula. I'll just throw those in there and get to 45. So he publishes that in 1771. In 1780, we don't talk about that one because he added 23 more, but then a year later than after that, he and Pierre Méchain collaborated a little bit to get that number up to 103. That was where the number stood for the longest time, certainly in his lifetime. But in the 20th century, various people added on new ones. There's no formal process for this, but I guess we've all agreed that the modern Messier has 110 objects in it, because we've added 7 more. And these are based on either things that Messier had written in his own copy, or letters between him and Pierre Méchain, or in a couple of cases, places where he had drawn a picture of them and didn't include an explicit number. We've all kind of agreed that we're going to stop at 110. The Messier catalog really doesn't need to grow anymore. And you can see on the right-hand side, I just sort of put the ratings that I had arbitrarily given these objects. And yes, there are a lot of really amazing objects in this catalog, and you're probably well aware of that and seen a lot of them. Some of the strange ones, though, type of objects you don't see in other catalogs. So Messier has this M24, you'll see it referred to as a stellar cloud. Really, it's a bright patch of the Milky Way that he decided to catalog as an object. M40 we discussed a little bit. M73 is the second least interesting object in the Messier catalog. It's 4 stars. The saddest thing about M40 and M73 is that not only are they not interesting visually, they're not even proper clusters. They're actually at different distances. So we think that M40 is a chance visual alignment of 2 stars. M73 looks like a chance visual alignment. Maybe 2 of those stars are together and the other 2 are twice as far away. They just happen to line up this way. But not even astrophysically proper. M40, he gets a lot of grief for this. This actually wasn't his fault. This was a well-known thing. So he was bringing in data from someone else's catalog, and even Messier acknowledged it wasn't the way. You're probably well aware of these objects. So that's M31 and M33, M51 and M42. These are just, some of the best objects in the night sky in the northern hemisphere. I will say M33 is particularly challenging. You're probably aware of that. It's got very low surface brightness. It's hard to image, but totally worthwhile. For my money, my favorite object from an imaging perspective is M78. I rated very highly objects that had a mix of things. So here in M78, you have color contrast, right? You have a blue reflection nebula, blue and white. You also have ionized hydrogen and red. Beautiful color contrast. Then you have a dark nebula that splits right through it, right? So you've got where the places where the dust gets so dense that it's actually blocking the light. You have these Herbig-Haro objects and these little red spots here, which are really astrophysically interesting sort of protostar type objects. And it just creates this amazing vista.
Question,
Yes.
how do you decide what color to put on these objects? I mean, to look up there and it's all white, black, and it comes out like this. How do you decide what's red, what's blue, what's
I didn't
dark?
decide this. These are the colors, but your eyes are, so this is a regular RGB image actually. So this is not H-alpha enhanced. So if you expose long enough, the colors will reveal themselves. Now, obviously in imaging, we boost the saturation and things like that.
Right.
This is true color, this one. The nebulae you're gonna mostly see are matte color. But because the rods in your eye are just not, the cones in your eye are just not that sensitive, when you have low light, you can't really perceive much color. It just takes a lot more color. But these are actually true colors. They're boosted. It's fair to say, like, if we did have more sensitive cones in our eyes, they probably wouldn't look this punchy, so to speak. And I'll talk about the nebulae in a minute and how we map the colors, but yes, all the galaxies, and reflection nebulae, dark nebulae, these are all true colors. I didn't modify the colors in any way. If there's an overlooked Messier object, I'd nominate it in M83, but that's still a pretty well-known galaxy. Okay, the new general catalog, NGC. 7,840 images, or entries, sorry, but almost 300 of those are actually duplicates. William Herschel was an unbelievable discoverer, so much so that people didn't even bother to try to discover objects during his time because he was just cranking out so many of them. But he was the first to say, I'm going to systematically go through every bit of sky I can see. He discovered 1/3 of the NGC with the assistance of his sister Caroline. His son John followed in his footsteps, traveled to the southern hemisphere, and added 1,700 more objects, leaving very few areas of the sky that didn't have objects discovered by the Herschel family. I've dubbed this, there's a couple areas called the Herschel holes where they didn't spend much time for various reasons. I'm not sure if this is where the trees in their backyard blocked their view or something like that, but there are a couple areas that the Herschel did not systematically scan as much. And you'll actually find other discoverers sort of filled in those holes, but they picked out almost all the good stuff everywhere else in the sky. Some people you might not be aware of, Albert and Park, and Lewis, I mean, Swift probably you're aware of, but these are people who contributed several hundred objects to the NGC. But these were all just piling up in various papers being published, letters between astronomers, and poor Dreyer had to come in. He was tasked with the Royal Society to come in and just take, what do we actually have? Can we put all of this into one catalog? Oh, we got people's letters scattered all around. So he spent a decade or more actually trying to synthesize this into one work that we now call the NGC. The guy was getting, varying quality of data from different people. It's not his fault. So that's why there are, several hundred duplicates. And we've spent 2 centuries basically cleaning all of this up. With almost 8,000 objects, there are some many highlights. These are the ones on the left that I rated 5 stars. These go from the northern to southern hemisphere, but you're probably aware of most of the ones pictured here. And here's the first of the matte color nebulae. So this is a case where these are not the true colors. So these 2 objects here, I have done the typical Hubble palette mapping, where they represent something, the colors represent something true about the object, in the sense that sulfur is mapped to red, hydrogen is green, and oxygen is blue. So where you see those colors, so for instance, where orange and yellow, this is a mixture of sulfur and hydrogen gas. Where it's blue, that's primarily ionized oxygen. So it's representing something true, but that's not the colors you would see. Interestingly, in the case up here, the Veil nebulas, those are mapped hydrogen and oxygen only, with oxygen blue and hydrogen red. That actually would be very close to the true colors you'd see. Again, if your cones or human cones were like that. Some overlooked objects potentially. This is NGC 1333. This is a beautiful object that requires really dark skies. Anytime you see these like chocolate milk kind of dust look in an image, those kind of molecular clouds which seem incredibly faint, requires dark skies and long exposure. This is a very difficult object. One of my favorite objects, the Angel Nebula. Again, for me, this scores a lot of points because you've got this beautiful electric red hydrogen, you've got the browns of the molecular cloud, you got the streaks of dark nebulae, just a lot going on visually. I think it's a very aesthetically pleasing object. Also requires very dark skies. Some galaxies, NGC 3486. You don't see a lot of galaxies like this. This is somewhere between actually a normal grand design spiral, and it's transitioning into the flocculent style of galaxy, but it has at least 12 arms that I can count. And so as it evolves, those arms just become almost blended into each other into what we call a flocculent style, like M63, where it just looks like it's, and flocculent means like plucked wool almost. You sort of get that textured approach to a galaxy and its arms. This is a very cool colliding pair. I like this because these 2 galaxies are in the process of colliding, and you can see it for the first time because they haven't completely disrupted each other yet. And when galaxies collide, they don't actually physically collide because there's just so much space between stars. They pass through each other, but all all those stars passing past each other throws their, they pull on each other gravitationally, and you'll get these, tidal streams, we call them, of stars that have been ripped out and sort of flung out into the space between the galaxies. This is just cool. This looks like they're just doing a head-on collision right now. Planetary nebula, NGC 5189. This is an interesting one because I think it looks really cool. This is the same object shown from two different telescopes. So this is a type view of it. And it has a really neat, this very intricate figure 8 bipolar structure. And this is where I've mapped oxygen to blue. And then you can see it's got a little bit of hydrogen in red on there. Then you can zoom out and take a look at a wider field of view and see that it sits among this huge sea of ionized hydrogen, which you showed red here. And there's actually another very faint planetary nebula you can see down there.
Wow.
It does, yeah. Yeah. We can't help but see animals, it seems like. You could make a list of like the 100 objects in the night sky that we see different animals in. The index catalog. Okay, so you've heard like the NGC IC, right? So the index catalog, drier body was done. The poor guy cataloged 7,840 objects. He's like, that took me over a decade. I'm going to relax. The Royal Society comes back and says, well, we've had, while you were doing that, people started applying photography to astronomy. And now we've got all these new objects we want you to catalog. Okay, so I'll do it again. He spends another, I think, almost decade working on the IC. And the IC has, it's another 6,000 objects, but early photography wasn't that sensitive. So it didn't discover a lot of big, faint things. It discovered a lot of small, more condensed and bright things. So it's primarily really small galaxies, less than 5 arc minutes. So there's not a ton of, percentage-wise, not a lot of interesting objects. Testament to the Herschels, they only discovered 8 additional globular clusters. The Herschels have picked them all up. Like, it was amazing the work that they did. So there's nothing left to discover in the IC in a lot of ways. So I date myself, but the story here is that there was a boxed set, the greatest hits of Led Zeppelin, when I was a teenager. It was like, oh, that's great, on 4 CDs. And then they issued, a couple years later, they're like, well, here's all the other Led Zeppelin songs. We're going to put those in a different box set. I don't think many people want this one because it's literally all their worst songs on one thing. And I feel like it was the leftovers. The IC is the leftovers of the NGC IC. And it had a ton of erroneous endings. So 1,200 objects were duplicates. They were miscategorized things or had coordinates that like the person submitted and we'll never find the object because we don't know what they were talking about. So lots of errors in it. That said, it does still have some pretty incredible objects in it. So these are the 5-star objects I pulled out of that. And these are some you're probably quite familiar with. The elephant trunk, the heart, the soul, witch's head, Horsehead Nebula got its designation from the IC. Tadpoles, flaming star. Like these are amazing objects for astrophotography. And primarily, you look at these are mostly big, faint nebulae that work well with narrowband astrophotography. The great thing about narrowband is that narrowband, for reasons we have to get into in a different talk, allow you to image quite well in light polluted areas, right? So if you have narrowband filters, this is what you can do from light polluted areas. And in fact, I think all of these are from my backdrop, which is like 405, but not particularly faint. But there are, somebody wrote to me, they were in an apartment in Singapore and sent me pictures they'd taken of some of these objects from their, it's like, I don't know what the worst portal you could possibly have, but the most light polluted place on Earth, and they're able to use narrowband filters to still capture some of these new things. Some overlooked ones. These are particularly objects. These are commonly referred to as Orion's tears. They're little tiny molecular clouds, and this does require dark skies. But these 2 bright stars here are 2 of the belt stars of Orion. And if you are able to have good enough optics that the glare doesn't get you, and dark enough skies that you can actually reveal them, they're these really neat little molecular clouds. SH2 might be a number you've seen if you're an astrophotographer. So this stands for Sharpless's second catalog. This is where all the nebulae the big H2 regions in our galaxy show up. And these were taken, this was the culmination of work by a lot of people done in the 1950s. We started trying to capture with these narrowband filters for the first time, these very large objects. And this was actually, technically, this was a narrow red filter used by the Mount Palomar telescope. And again, these are some amazing astrophotography targets. You're probably familiar with some of these. This is the Wizard Nebula, Cinis 147 up there, the Spaghetti Nebula in the upper right. But these are very common for astrophotographers to look at. These are really challenging if you're trying to look at them through an eyepiece. Some of the more overlooked ones, Sharpless 34. This is a huge object. I say this one suffers from having famous neighbors. It's right near the Trifid Nebula and the Lagoon Nebula. And so people go to those, but there's this other really interesting, not quite as interesting, but very interesting, very large, and from a narrowband perspective, very bright object in Sagittarius, Sharpless 34. This is one of my favorite objects, Sharpless 126. I call this the scarlet letter, it's a big scarlet A, but the red is showing you the ionized hydrogen, but it is twisted up with molecular dust, so non-ionized dust. This requires taking a narrowband image in hydrogen and then supplementing that with regular RGB data and a lot of it, and hopefully under dark skies, to reveal these molecular clouds that are sort of entwined with it. Sharpless 119, sometimes called the clamshell nebula. So this sits right next to the North American nebula. It's much fainter, but it's huge, it's beautiful. I think it's a stunning object. I think it does look like a clamshell. It's got a pearl in the middle of it. Again, we tend to want to see animal shapes in these objects. Planetary nebulae, so this is Sharpless 216. This is the second closest, I think, planetary nebula to us, and so that's why it's so large. It's actually, most planetary nebulae are really tiny. So it's actually, I think, about a degree in size. It's very large, but it's also very faint. These are all taken with narrowband filters. Sharpless 263, I think someone's called this the Strawberry Nebula. Again, challenging because you have all this molecular cloud here. You got a reflection nebula, but you've also got ionized hydrogen there. So it requires combining narrowband filters and RGB data to capture the full extent of the color that you can get there. Sharpless 280. This one sits right under the Rosette Nebula, and nobody ever looks at it. It's actually almost as big as the Rosette Nebula. It's huge, and you can see it takes a little while, but you can see with enough exposure time, you can reveal the blue ionized hydrogen. Now, Sharpless was only able to catalog objects down to about 27 degrees south. So a group, RCW, Rogers, Campbell, and White Oak, picked up from there and went further south. They were imaging from Mount Stromlo in Australia, and they used, I love this, an F1 telescope. And they were able to accomplish that. You won't find F1 telescopes these days, but you could do that with a Schmidt telescope, because what they would do is it had a curved field, and you didn't have a flat field, so they would take the film and it would stretch the film into the right shape so that it was all in focus. So you had to had a suction plate that held and stretched the film into inside of a sphere, basically, and they were able to capture these really deep images. And their goal was to do what Sharpless had done and look at ionized hydrogen in the sky in the southern hemisphere. So here's some interesting objects there, RCW 58 and RCW 54 is particularly pretty there. If you heard the Vela supernova remnant in the southern hemisphere, it extends, I don't know, like 10 degrees at least. It's huge. And then there's just a particularly beautiful, so the red part here is actually the RCW object here, 35. And then again, as I talked about earlier, you get some objects use this nice sense of depth where there's this branch of the Vela supernova remnant and ionized oxygen in the front, and then sort of behind it, this more diffused red thing. Leads to a beautiful color combination. Some more RCW 85. This is really, really far south from the sky, but you know, we've been able to a lot of from the northern hemisphere. a unique one that I like. This is called the Dark Tower. And again, since a 3D structure to it, where you've got what appears to be this pillar of gas and dust obscuring the starlight behind it. And it's sort of shaped the cloud. So you can see the shape of the cloud that it's in, but there's all this ionized hydrogen and red around it. If you looked at reflection nebulae, you've seen the Vandenberg catalog. Vandenberg, he discovered a lot of objects from the 20th century, but this is the catalog he's most known for. He scanned over 50,000 stars to identify 159 objects. So these are reflection nebulae around bright stars. A couple examples there. This is the Antares Nebula. This is one of the few yellow reflection nebulae in the sky. This is in the Ro-Ophiuchi area. And then Wolf's Cave. So this is actually nicely visible here in the northern hemisphere, but again, requires fairly dark skies to see. And the actual Vandenberg is just this reflection nebula right there. This is also taken from my backyard with a lot of exposure time. Vandenberg 14 and 15. Vandenberg 70. This is one that I think I actually have currently the deepest image on this object. It doesn't get much attention. I can't remember. This is probably 15 or 20 hours of exposure time on this. And then you saw earlier the Angel Nebula. So you can see how they relate in proximity to the wider field of view. Vandenberg 80, quite nice. Again, it gets points for the multiple colors, color contrast. Vandenberg 16 up at the top, and then there's some Barnard objects. We talked about the Barnard catalog of dark nebulae earlier. They tend to, have these large groups of them in these high density areas in the middle. And then you've got so basically what's happening here is you have dust, and it's in interstellar space where it's getting so dense that it obscures what's behind it, and then sometimes it thins out and it's near a bright star and you get a reflection nebula. So it's the same dust cloud behaving in an image two different ways. The Abel catalog of planetary nebulae, again, based on the Palomar data. These are very difficult objects for the most part, but there are some very pretty planetaries you can image out there. All out best in the book. And they're quite small, so it's the second reminder that you need to get another telescope. You need excuses, I'm happy to be here for you. The Barnard catalog, we talked about how difficult this was. Barnard was a perfectionist though, and he was doing amazing photography. I tell people he, to the best of my knowledge, is the first astrophotographer to take multiple nights of data. That's trivial to do now. I'll include 20, 30 nights of data sometimes in an image because I can put them on a computer and synthesize it. In the film days, you couldn't do that. But Barnard would take, manually track the whole night on one plate, shroud everything, keep it incredibly dark. 2 nights later would be the next clear night. He would realign his telescope and mount, point at the same object, and then cover everything, keep it coated in the same film plate another night, which is an incredible level of dedication. When he wanted to publish this book of dark regions in the Milky Way, and he was unsatisfied with the halftone reproductions that they had in the early 20th century. And so he insisted that we actually print, like physically, wet process print every image in the book. And he did a print run of 700. So I don't remember how many pages, like 60 or 100 pages in this thing. And each one of them in the originals is an actual photographic print that Barnard prepared. That's why, if you get a used copy of this book, they're about $10,000 right now. Also, I should mention, he was such a perfectionist, he couldn't get that done, and he died, and his cousin or niece had to carry it on and actually see it through after he died. This is an example of, this is an image taken from my backyard. This was a real struggle though. This sort of object would be much better served under darker skies, but it does go to show that even under relatively light polluted suburban skies, with enough exposure time, you can actually pull out some of the darkness. We talked about the supernova remnants earlier, and I've tried to include in the book every supernova remnant that has an unknown optical component, because most of them they're all pretty much all discovered via radio telescopes. There are some really interesting ones. People call this the Beta Fish Nebula. I'm not even going to read its name because supernova remnants typically just go by a big long string of digits. Those are their galactic coordinates. But really interesting to see these tiny tendrils. They're very faint, but very fine features. This is in central Cygnus. So this will be coming into view right about now. To give you a sense of scale, this is a 4-panel mosaic, but that circle in the upper right is the size of a full moon. So just to give you a sense of how big, this object is not small, it's difficult to image because it's so faint. I think this is about 40 hours of exposure. Another beautiful supernova remnant, this one's a little further south. Cometary globules might not be even an object type you're familiar with, but because they're mostly in the Vela region in the southern hemisphere, they're really interesting because they all have a similar format where they basically what's happening is you have this molecular cloud, a star is forming oftentimes in these incredibly cold Bach globules in the front, but there is some sort of stellar wind, if you will, that is pushing outward on them. And so if you put them on a very large map, you see that the heads all point toward one region, which is two nearby regions in Vela. And that's where there was the giant Vela supernova. I don't remember how many millennia ago, but that outward pressure is stretching them out. And so you form this head with a tail. Favorite of all CG4 over here is called the galaxy eater. Obviously, these things, so this CG4 is in our own galaxy. It's forming this hand-like or mouth-like structure. And there's a galaxy up there. That galaxy is millions of times further away, but the chance alignment in an image makes it look pretty cool, like it's reaching up to grab it or eat it. CG31, I think, is a particularly pretty one. And again, you've just got dust and gas behaving in ways that both block light and then emit light. Last couple catalogs, Lynn's catalogs. She was using the Palomar Sky Survey plates. Again, as she was saying, well, let's go through and try to capture all the nebulae people in the past have missed. Particularly cool ones here, I like the Gecko Nebula. This is also challenging because, again, you've got this ionized hydrogen feature, but also molecular clouds in front of it. Great color contrast in this area. This is 902. And the blue again is oxygen, the red is hydrogen, and a lot of the things between are just dust. This is in Cygnus, this is LBM 331. Again, another object that I think gives this nice sense of depth. It's almost like a piece of saran wrap or something that's laid out in front of you, edge on. I like this one. I think it looks like a check mark. That's all I can say about that, but this one requires a lot of dark, very dark skies to reveal. LBM 640, I think there's nothing else quite like it. You just have these two intertwined, almost like tadpoles or something, but it just has a structure that looks like nothing else in the sky. And then we've got the Large Magellanic Clouds in the southern hemisphere. So if you're lucky enough to go to the southern hemisphere, or I haven't seen them with my own eyes, but I have a telescope down there and I can take pictures of them. There's some pretty amazing objects there. This is a 20 panel, 24 panel, I can't remember, mosaic that I took with my collaborators from with our scope in Chile to capture the main nebulae in the Large Magellanic Cloud. And you can just see again, this is oxygen in blue, hydrogen in red, and it's just a total chaotic mess. The amount of star forming and star exploding that is going on in our companion galaxies is ridiculous, and it's so much so that these bubbles are colliding with each other and creating these crazy shapes. But the most well-known objects down there, certainly the Tarantula Nebula on the right, is massive, it's bright, it's big in the sky, and it's just all these overlapping bubbles that just it looks like they just all popped at different times and creating this crazy structure. And then finally, objects from catalogs you may have never heard of. Setterblad catalog, Setterblad 51. Fairness 147. This is in the southern hemisphere as well. I put this reminder up here. Your Buddha gang, sorry, your Buddha Ian. It's Gulbudagian, sorry, Gulbudagian. I put that up there and I still mess it up. And the cool thing about this is it's a variable star that is illuminating it, and its illumination varies year to year. So I imaged this 2 years ago, you might try now and you might not see it at all. You might try in 3 years and it looks way, way brighter. But this whole right area here with this arc that comes out from it, in some years this is almost invisible. Grand 56, people call this the Misty Mountain. This is part of that giant gum nebula. Remember I pointed out on the map of the sky, that giant gum nebula on one of the first slides. You zoom in on the middle of that, there's this really cool structure that is revealed. This is visible to us in the northern hemisphere. This is in Cygnus. This is the Longhorn Nebula. Some interesting galaxies. There are some of these ring galaxies out there. And again, I took all the images in this, or collaborated with other people on them. And we used almost exclusively 5 and 6 inch refractors for this. These are very small. I encourage you to go look up the Hubble images of these, but it's pretty cool though. Even with a 5 inch refractor, you can still pick up a few of these ring nebulae. Sorry, ring galaxies, my bad. Henneis 2111. I'm actually going to go back in this summer when this comes back into view in the southern hemisphere and gather more data. I didn't gather nearly enough. I think this was like 10 hours of data. This object deserves like 40, and I'm going to go back and get it because I think there's a lot to be revealed in this, and it's a very rarely imaged object. HFG2 is a Wolf-Rayet, around the Wolf-Rayet star. I think there's a few of these. I call them the soccer ball planetaries. They kind of like a soccer ball or a brain or something like that. We have formation around them. There are a few of those out there. Wolf-Rayet 134 is this guy here, but what I showed it to you in is a wide field view, so you can see it's in the middle of Cygnus. It's right next to the tulip there. CTA1, Caltech Observatory Radio Catalog A is what CTA stands for. This was discovered in radio signal. This is 17 hours, and I'm just getting started on this one. It is really faint, but the optical component was discovered much later. Some other interesting objects. This is pretty neat. If you do some research on this, this is Arafuraei, and it's exploded multiple times, including 6 years ago. So you see one explosion, and then there's another explosion, another outburst in 1830, and then not visible here, but very close to the star, there was an outburst like 6 years ago. And each one of these is creating concentric shells, but they're at different angles because it's likely it's like a binary star, 2 stars orbiting around each other, and the outbursts get oriented in different directions because of that rotation.
Why does it look fuzzy?
Because, well, it has to do with a lot of reasons. It's quite small, so I've used a 5 inch refractor to image it, and so I only have so much resolution. So you can see here, you can often tell by the size of the stars how much I'm zooming in on something. So I'm pushing the 5 inch refractor to the limit. This background, however, is actually an artifact of the way Zoom is compressing my images down to 8 bits. And so I think it does some stuff in the background, or it tries to do some stretching to the image that this is not actually how the image looks in the book or on the app. This is just a function of the web presentation. Baroness 147, again, you got a really cool reflection nebula in blue, dark nebula, gas, super dense stars in the background of the Milky Way. That's a particularly beautiful object. And then there's a few objects, believe it or not, they don't have catalog designations. So the Coalsack doesn't have a proper designation. There's a place with a Serpens Nebula. It's just, you look it up, the official astronomical designation is Serpens Nebula. And then the red rectangle. Technically, it does have a super obscure catalog, but I like it because it's the only rectilinear. There's only like 1 or 2 objects in the night sky that it just, for various functions of the way the explosion happened in a bipolar planetary nebula, it actually looks somewhat rectangular. And then some are just really interesting because they're hard to image. So this is the Fornax dwarf spheroidal galaxy. There are there are a few of these dwarf galaxies. They're incredibly faint. And if you have to really push hard to see them, but they do look kind of neat when you image them, but they require really dark skies and you can only see them with telescopes with a camera attached. So the final question, after going through all that, you ask yourself, is astrophotography a hobby where I'm going to run out of objects to image at some point? I would suggest that's very unlikely. So even of the 1,700 objects I looked at, I ended up rating 984 of those 3 stars or better. And my hypothesis is that if you were to try to image all 984 of those, by the time you got to imaging the last one, your skills and your equipment would have improved, and you would just go back and want to shoot them again. So my answer is that I think astrophotography is a hobby, certainly that could keep one busy for a lifetime. This is just to show you what the result of all that work was. These are some of the pages from the book for I'm going to show you. So I did the rating and the write-ups on each of these objects. Again, it's like what I spent basically the past 5 years doing. And then my partners at Nature Guides have translated this into an app, also just called the Astrophotographer's Universe. But this is a labor of love for me for the past 5 years since COVID, and I'd be happy to take any questions.
You have anything projecting onto a glowing sky? You know, so see some of the sizes of these nebula, and some of them are so large.
Yeah. So, how do you mean project?
Well, like, it's a sphere up
Mhm.
there, and you can project that flat,
Mm-hmm.
and with the actual size of the nebula and everything.
So yeah, so that's what that image I showed you was. And I have posters over here available for sale as well of that image. So yes, anytime you take a curved surface and you project it onto a flat thing, there's gonna be some kind of compromise in terms of distortion. And that at least does give you a sense of the scale. So I showed you like the Pleiades or like a tiny little thing on there. The problem is that the scale varies so widely that you've got objects that are like let's say M31, the Andromeda galaxy, that's 3 degrees across. And then you've got hundreds of galaxies that are 5 arc minutes across, right? So they are, many orders of magnitude smaller. And so the difference in size is so enormous that if you project one of them, like if you're looking at the Andromeda galaxy, the planetary nebulae are just so small, there's like 1 pixel or something in that image, right? There's just really dramatic differences in size. I do actually sometimes, I do have a different presentation, where I've done exactly what you're saying, which is I show the full moon at one size. And then I just overlay 5 or 6 or 7 different objects to show the sense of like the ring nebula. And it's like this teeny tiny little thing. And then I show one of those supernova remnants I showed you before, and it's like way bigger than the full moon to give you a sense of scale. Yes, I don't have that presentation here.
If there's no questions in the room, there's a question in the Zoom. Are all of the images taken in monochrome, or do you use an OSC sometimes?
Great question. I think one image in the whole book might have been taken with one-shot color. I use monochrome because you really need to properly do narrowband imaging. You really need separate filters rather than like the dual band filters. So yes, it's a little more work because if you're taking a color, just normal RGB object, you have to take a red, a green, and a blue filtered image, and then you have to take the time in the software to combine that into a color image. But yes, they were almost all done with monochrome. Yeah.
Are all of your books available on Amazon?
Yes, they are. I have some of them available for less than Amazon, but they're all on Amazon.
Hey, look.
Yeah, please do. Yes.
So I noticed you're using high-end refractors,
Mm-hmm.
and for similar sort of price, you could have got a much larger reflector.
Mm-hmm.
Why that choice?
Great question. Because if I have a scope that's remote, it's difficult to intervene. So like like collimation, things like that. I have to pay the sites that host the telescope to go out and collimate. So I want something that is as low maintenance as possible. And so the large refractors tend to be that. I some of the really high quality reflectors, I think, so when I visited Utah Desert Remote Observatories, there were a couple of like really expensive Newtonians there, but those are designed for imaging. They cost a lot and they're designed to like hold their collimation extremely well. But yeah, I didn't want something that in transit to the site was going to get, you know, the mirrors out of alignment or something like that. In fact, if you the other scopes, there are refractors or reflectors there. They're corrected Dahl-Kirkham CDKs. That's a very popular large telescope to put. Those scopes hold their collimation and alignment incredibly well. But for instance, if you buy a plane wave CDK and have it hosted at Utah Desert Remote Observatory, plane wave sends a technician to go set it up because like they might have gotten, they're so sensitive, they might have gotten jostled in transit. So short answer is that refractors were just a low maintenance approach for remote observing.
A question from Jeff Beck, who's our membership and outreach chair
Yeah.
online. What is the size of the telescope?
Great question. So in Chile, we have a Takahashi TOA 130. So that's a 5-inch refractor. In my view, that's, I mean, it's the sharpest refractor in the world. I can't think of anything better other than the fact that Takahashi is coming out with a new line, which is even more expensive. It's supposed to be even sharper. But under the skies in Chile, regularly has 1 arcsecond seeing, which is just incredibly sharp, clear skies. We put that Takahashi TOA 130 there, and it reveals more than my 10-inch reflector from my backyard in Pennsylvania reveals by far. Like it's way sharper. So we have a 5-inch refractor in Chile. My scope in Utah is a 6-inch refractor, a Tech 160 in Utah.
Is there a telescope in Chile located in the Atacama Desert?
Not technically, but it's right near there. It's a Rio Hurtado, so it's the next little area over. I know you can see on the next horizon over is I think it's the Nancy Grace Roman telescope. So like from that site, you can look off in the distance, see there's another big mountain out there, and you can see some of the big famous you know, Atacama type things. But yeah, it's effectively there.
Yes, because I was there almost 7 years ago,
Yeah.
and we visited the Alma Radio
Yeah.
Observatory as well, so.
It's quite a bumpy truck ride up into the desert, I hear.
Well, we had a bus ride mostly up to the observatory area. And then I guess we took a truck from there.
Yeah. Did they have like oxygen ready for you?
They had standing by, we were out for a little, we did feel heavy.
Yeah.
You know, it was noticeable, we didn't go up to the upper level platform, but they actually had the telescopes. We were just in the observation station where the offices set up, so.
Yeah, it's, I didn't get to go, my co-author actually just wanted to scope down there. It's pretty amazing for the fact that remote telescopes it's expensive. But if you're gonna do it, a place like Chile where we get something like 250 good clear nights a year. To your point, it's at like 8,000 feet, so the atmosphere is very thin anyway. The seeing tends to be amazing, and it's pretty close to pitch black, as you probably, were you there at night? Did you just stay?
Yeah, we did see, there was a lady astronomer who gave a presentation. She had a 16th Orion telescope that she showed some objects on.
Yeah.
And
Probably looks better than your backyard through this.
oh, much, we had the whole Milky Way in view too.
Yeah.
From there, she took some picture of us in the background with Milky Way in the background.
That's crazy that she could just frame the Milky Way in the background.
Stayed at the village of Atacama when we're there too,
Yeah.
so.
Yeah, so this is something like 40 miles, I think. Okay. All right. Thanks so much. Well, thank you for having me. It was great.
Thank you. Do you think you brought some things to look through?
Yeah, so if you're interested in purchasing any of my books, I've got a few copies here.
I don't know stuff that I don't know, lifetime left. Investigated or.
Sound of what you use.